As usual, I have some videos. It's a kind of introduction, or rather another view on the topic. You don't need to watch this introduction before going into the lecture. In fact, we will not watch it over Zoom. You will watch it whenever you like and see another exposure of Vertex cover. There is also a video on matching and independent set and other things. Anyway, as I mentioned, logistics can be viewed as the art of delivering services and serving the resources with serving the demand with the available resources. And Vertex cover is one of such covering problems that shows up quite often in logistics. Similarly, matching is yet another problem that shows up quite often in logistics, maybe more known under the name of assignment. You know, you're determining which goods will go from which warehouse to which store, or which people will receive certain services, or which passengers will go in different buses or airplanes or whatever. So all these questions, when you're assigning things among themselves or assigning one set of things to other set of things, is an instance of the assignment problem, or sometimes called also matching. So formally, what are we looking at? So one important thing is that now we are switching to undirected graphs. You remember when we were considering shortest paths and flows, the edges of the graphs had directions. They were directed one way or another. Today we will be looking at undirected graphs. So, no arrows, or if you want, all the edges in the graph represent two-way streets. But really, we will not be talking about streets or any other transportation-like things in the graphs. So our graphs, instead of represent transportation networks, they will just represent some relations among nodes. So think like in a social network. So nodes could be people, connections could be mutual friendships among them, and so on. Or the nodes could be some goods, could be some jobs, and well, certain things are connected among themselves, and these connections are indicated by the edges in the graph. And just to remind you, we will not be using the adjacency matrix, adjacency list, or edge list, and other things. But just to remind you, the adjacency matrix is the matrix, square matrix, which has as many columns as there are vertices in the graph, and as many rows as there are vertices in the graph. And every edge is represented by a 1 in the adjacency matrix. So if there is an edge between node 1 and 2, then you have a 1 in the first row in the second column. And for undirected graphs, the graphs that we consider today, such a matrix is symmetric. So if you have a 1 in row 1 and column 2, then you also have a 1 kind of symmetrically about the diagonal in row 2 and column 1. So as you can see, this matrix is symmetric. Whenever there is a 1 in the ith row and jth column, there is also a 1 in the jth row and ith column. So again, we will not be using it today, but just to remind you what it is and what's the difference between undirected graphs and directed. So two things, two notions that we will study first before going to independent set are the notions of the vertex cover and the matching. Okay, so vertex cover is a subset of vertices. Okay, so you have the vertices in the graph, and well, in this case, maybe these 3 green vertices are a subset of vertices. The subset of all vertices of the graph we denote it by V. So these are all vertices, and some of them, like the green vertices over here, the 3 green vertices, are a subset of all the vertices in the graph. And the subset is called a vertex cover if any edge in the graph, no matter which edge in the graph you take, any edge in the graph is incident to at least one vertex in your subset. Okay, so the subset of vertices is called a vertex cover if it quote unquote covers all edges, meaning that no matter which edge in the graph you take, at least one of the endpoints of the edge will be incident to the vertex in the cover. So you can check for this graph, every edge is incident to at least one vertex. This edge is incident to green vertices, to the vertices in the vertex cover on both ends. That's fine. Other edges, I think all other edges have one endpoint covered, but there is no edge which would be uncovered by the green vertices, where again, covering means that the edge is incident to a vertex. So you may think of this, you know, if you still think about the edges of the graph as, let's say, roads and or corridors in a building, and let's say you want to install cameras in the building or somewhere in the intersections of the roads, and you want to be able to see from your camera every road. It means that no matter which road you take, there must be a camera at one endpoint or the other endpoint, or at both endpoints. Both endpoints are fine too. Okay, so that's the notion of the vertex cover. Here is yet another definition. Yes, for every edge UV in the set of edges of the graph, either one endpoint or the other endpoint of the edge belongs to the cover. Maybe both endpoints belong, that's also fine, but at least one endpoint must belong to the cover. Okay, so again, to summarize, vertex cover is a set of vertices such that every edge has at least one endpoint in your set. Every edge is covered. Any questions about this definition? So we'll have more and more examples, lots of examples of vertex covers, of course, and we will be working with them a lot. Okay, switching to the next definition of the matching. Now, the vertex cover was a subset of vertices, and matching is a subset of edges. Okay, like these blue edges over here, 1, 2, 3. So a matching is a subset such that there is no vertex at which you would have two edges in the subset coming to that vertex. Okay, so for any vertex in the graph, at most one edge from the matching is incident to it. Or here is yet another formal definition. For any vertex in the graph, there are no two other vertices. So for any vertex V, you will not find two vertices U and W such that both this edge and this edge are in the matching. So this is bad. So these two red edges cannot simultaneously be in the matching. Again, a matching is a set of edges such that no two edges from the set share a vertex. Yet another reformulation of the same definition. So like these blue edges, you would never see two blue edges come into a single vertex. Okay, that's the definition of a matching. Now, what is interesting, now we're coming after these definitions, so we know the definition of the vertex cover, now the definition of the matching. Now let's look at some problems that are associated with vertex covers and with matchings. So for the vertex cover, it is interesting to find the minimum vertex cover, right? So imagine that you want to install smallest number of cameras to watch over all of your corridors or all of your roads. Of course, one possibility is to install a camera at every single vertex, but that would be too many cameras. What you want to do often is to minimize the number of vertices in the cover, to use fewest resources in order to cover all the demand. So the demand here are the edges of the graph, and the resources are the vertices, and you want to use fewest resources to serve the demand. I mean, super standard logistics or whatever problem, super standard optimization problem, finding minimum vertex cover. Okay, you want to find a vertex cover that has as few vertices as possible. Unfortunately, there is no efficient algorithm. We will not be studying any algorithms to find minimum vertex cover, but we will do some approximation. But again, the important thing is that you want to find the minimum vertex cover. You want to minimize the number of vertices that cover all the edges, that altogether cover all the edges. For the matching, on the contrary, what you want to do is to find the maximum matching. So one very simple matching is the empty set. You know, if you don't choose any edges in the graph, then of course you will never have a situation when two chosen edges come to a single vertex V. You know, like this is a bad situation for a matching if you have two edges come into a single vertex. While if you have an empty set of edges, that's a matching, because no two edges from the set touch a single vertex, because there are no edges in the set at all. But that's not a very interesting matching. So what you want to do is to find maximum matching. Again, thinking of matchings as assignments, you may want to assign as many people or to each other, or as many jobs to the worker. So whatever, you want to do as many assignments, as many matchings as possible, and hence usually the goal is to maximize the matching, or at least that's the interesting thing. The interesting thing is to find maximum subset of edges, no two of which share a vertex. So actually for finding maximum matching, there exists an algorithm, but it's quite complicated. We'll not consider it. We will do something simpler. But anyway, the important things are here, well, other than the definitions, the vertex cover and the matching, the important things are that when we are talking about a cover, we want to find the cover with minimum number of vertices in this case, or in general with minimum number of resources. When we are looking for a matching, the interesting thing is to find the maximum matching, the matching that kind of does as many assignments as possible, or serves as much of the demand as possible, or whatever the specifics are. Okay, any questions over here? If not, we go to the next slide. As usual, I have very few slides, but a lot of information on each of them. Well, here again, a video which yes, asks you to find the minimum vertex cover in a simple graph. We will not go into it in the lecture, but you can see the video and see the solution. So here is the next important slide. Again, talking about covering problems like a vertex cover, and this type of packing problem like the maximum matching problem. So again, in the covering, just to repeat what we had on the previous slide, you want to find the solution with the minimum use of resources, or when we're talking about the vertex cover, with the minimum number of vertices that cover all the edges. And for the covering problem, usually if you just go all in, if you choose all the vertices, like, you know, if all of these vertices of this graph are in the cover, then of course every edge is covered. Actually, every edge is covered twice. Every edge is covered by both of its endpoints. So this is a feasible solution. You do the cover, you do cover every edge, but this is not a very interesting feasible solution. I mean, it's not optimal. Yes, the demand is served, so you know all the edges are covered, but the cost is very high. You have to use all the vertices, so you're using too many resources. But still, this is a common feature of the so-called covering type of optimization problems. This is the problem when you're trying to find a solution which minimizes the used resources, and usually using all the resources is feasible. Well, if it's not, then your problem is infeasible altogether. If even using all resources doesn't cover all the demand, then well, how can you find the minimum number of resources that covers all the demand? So using all resources is feasible, but not interesting, not optimal. And your goal is to find the smallest set of resources that covers all the demand. And this is juxtaposed, on the contrary, in the packing problem, you try to find the solution which maximizes something, maximizes the demand served, maximizes the number of assignments, whatever maximizes the number of edges in the matching. And here again, in contrast with the covering problems where taking everything in gives a feasible solution, in a packing problem, taking nothing or taking empty set is a feasible solution. Okay, like over here, here is a matching. Well, this matching has no edges. That's why none of the edges is highlighted. But it's a matching, to take this vertex, this edge is not in the matching, this edge is not in the matching, this edge is not in the matching. So there are no two matched edges that come to this vertex. And you look at any other vertex, well, there are no edges in the matching, so you will never have a conflict at any vertex that two edges incident to a vertex are in the matching. So taking an empty set is a feasible solution here and in general in any packing problem. But, well, this is not really interesting solution. It may be bad because, yeah, you avoided all conflicts. You never have, two resources serving the same demand or whatever, two edges coming at a single vertex. But you essentially didn't do any assignments. You have no revenue, or you didn't serve the demand, whatever. So again, the general idea in the packing problems is that in contrast to covering problems, in the packing problems, you're trying to find maximum solution, and taking the solution with 0 elements, the empty set, is a feasible but not optimal solution. Okay, so this is the kind of similarities, but also the differences between covering and packing. In the covering, you're looking for the minimum. Everything is a feasible solution. In the packing, you're looking for a maximum. Nothing is a feasible solution. And we are talking about minimum and maximum quite often. And very often we, just say min or max. It's just the usual abbreviation to say that min means minimum, max means maximum. I'm sure you have seen it also outside of this course. Now, something that may be new to you is the notion of minimal and maximal. And what I want to spend time on now, over here, explaining things right here, is the difference between minimal and minimum, minimal and minimum, and similarly the difference between maximal and maximum. Okay, so what is minimal? A minimal solution is a solution which is kind of locally smallest. You cannot remove any of the resources, or in the case of vertex cover, any of the vertices without violating the feasibility. So maybe the example tells you more than just the definition. So on this example, these 4 red vertices are a vertex cover, right? You can check every edge is covered by at least one vertex. Check, 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 check. So it's a vertex cover. These 4 red vertices are a vertex cover. And moreover, if you remove any of the vertices from the vertex cover, then you will definitely lose feasibility. So some of the edges will become uncovered. Like if you remove this vertex from the vertex cover, then this edge will become uncovered. So you cannot remove this vertex from the vertex cover. Let me clean up a bit. If you remove this vertex from the vertex cover, then this edge becomes uncovered. So you cannot remove that vertex from the vertex cover. And so on. If you remove this vertex from the vertex cover, well, these 2 edges both become uncovered. So you cannot remove this vertex from the vertex cover. And the last one, if you remove this vertex, then these 2 edges become uncovered. So you cannot remove this vertex from the vertex cover. So this vertex cover is therefore minimal because you cannot remove anything from it without violating the feasibility, without violating the property of the set being the vertex cover, without keeping an edge uncovered. Okay, so that's the notion of minimal. It's not necessarily minimum, because maybe in this graph there exists a vertex cover with fewer than 4 vertices, but nevertheless, even though this vertex cover is not minimum, it is minimal, because you cannot remove anything while still having a vertex cover. Similarly, the notion of maximal. Let's again speak in terms of the matching, but in principle, it applies to any kind of solution to packing problems. So a matching is maximal if you cannot add any edge to it while keeping the feasibility. Again, so these, the magenta, whatever this color is, so these two highlighted edges on this picture form a maximal matching. Why is it maximal? Because if you try to add any edge, I don't know, you try to add this edge, oops, you have a violation at this vertex. 2 edges come to it. You try to add this edge, you have a violation at this vertex. This edge comes to it and this edge comes to it. You try to add this edge, you have a violation both here, and so on. So any edge you try to add to this purple or whatever magenta matching, you will have a violation. If you add this edge, then you have a violation at this vertex, because you would have 2 edges in the matching coming to the same vertex. So thus, these 2 edges are a maximal matching in this graph. You cannot add anything without removing any of these edges and still keep it a matching. Okay, so these are the notions of minimal and maximal. Now, why we are talking about them in the algorithms course? Because, well, as I mentioned, there is no efficient algorithm to find, let's say, a minimum vertex cover, and there is no simple algorithm to find maximum matching. There is efficient but a complicated one. But if you're not trying to find minimum and maximum, but trying to find minimal or maximal, then you can do it very easily by, you know, greedily removing or adding, well, in the case of vertex cover, removing vertices. In the case of matching, adding edges. Or more generally, for the covering problems, you can find a minimal solution by starting from everything, like starting from all vertices, and removing the vertices one by one until you cannot remove any more. And similarly, for a packing problem, you can find a maximal solution by starting from the empty set and then adding the edges one by one until you can add no more. And by definition, you know that you will be at the maximal or minimal solution, which may or may not necessarily be minimum or maximum, but whatever. You still have some solution which you cannot improve, at least locally. Okay. So just to show the last thing on this slide, that, well, indeed, the minimal vertex cover, like this one, could be worse than the minimum vertex cover. So this is the minimum vertex cover. It has only 3 vertices. This is a minimal vertex cover. It has only 4 vertices. So this 3 is smaller than 4. So this minimum cover is better than the minimal cover. So we are not saying that minimal is necessarily the optimal, necessarily the minimum. And similarly, the maximal is not necessarily the maximum, as we can see on this picture. So here we have 2 edges in the maximal matching, but here on the same graph, we have 3 edges in the maximum matching. So remember, we are trying to maximize the number of edges in the matching. 3 is larger than 2, and hence this maximum is better than the maximal, but still, maximal gives you some solution which is feasible and, well, which is not necessarily bad. Okay, so let's have some examples right now. So again, I'm trying to do the minimal vertex cover. So here is, oops, here is, what's going on? I'm resuming the recording. So we will be trying to find a minimal vertex cover in a graph. And I'm just redrawing the graph from the lecture, but it doesn't have to be the same graph. So if I take all the vertices in the vertex cover, well, that's a vertex cover. And now I removed this vertex. Do I still have a vertex cover? Or do you see an uncovered edge? Well, most likely I still have a vertex cover. Of course, we can check that still all edges are covered. But one reason for that is that if you remove only one vertex, then you cannot have any edge which is uncovered, because when we had all the vertices in the vertex cover, then every edge was covered from both sides, right? All the vertices were in the vertex cover. And if I removed one of the vertices from the vertex cover, well, this edge is still covered by its other side. So when I remove only single vertex from the vertex cover, then I still have a vertex cover. Is it a minimal vertex cover, or can I remove some vertex that so that I still have a vertex cover? Let me put numbers inside the vertices so you can tell me which vertex can I still remove while still having a vertex cover. Let's try removing some vertices. How about I remove this vertex, vertex number 3? Is it still a vertex cover? Do I still have a valid vertex cover? Or is there an uncovered edge? I claim that, well, now this edge is uncovered. This is not in the vertex cover, this is not in the vertex cover, so it was a bad idea to remove vertex 3 from the vertex cover. Vertex 3 should stay in the vertex cover, it shouldn't be removed. How about vertex 1? Can I remove vertex 1 from the vertex cover? Well, if I do that, then this edge becomes uncovered. This is not in the cover, this is not in the cover. Bad. That was a bad idea to remove vertex 1. So let's keep vertex 1 in. Can I remove something else? I don't know. How about I remove vertex 5 from the vertex cover? Looks like all edges are still covered, right? There are two edges incident to vertex 5. This one and this one. And both of them are covered by their other ends. So yeah, it was safe to remove vertex 5 from the vertex cover. So we still have a vertex cover. Any other vertex that we can remove? So let's see if we, well, we know we cannot remove vertex 1. Let's try to remove vertex 4 from the vertex cover. Well, now this edge becomes uncovered. So that was a bad idea to remove vertex 4. Vertex 4 should be in. Can we remove vertex 6 from the vertex cover? Yes. Both edges incident to vertex 6, this one and this one, are still covered from their other ends. So yeah, removing vertex 6 was fine. So now I guess we cannot remove any of the vertices. If we remove vertex 1 or vertex 3, then either this or this edge becomes uncovered. And if we remove this vertex, vertex 4 from the cover, then, well, I guess quite a few edges become uncovered. So we cannot remove it. So yeah, this is a minimal vertex cover. Okay, so again, this is a minimal vertex cover, which actually happens to be also the minimum vertex cover, but we are not really trying to do minimum vertex cover. The vertices 1, 3, and 4 are a minimal vertex cover in this graph. But again, the main idea here was not to find out whether that these three vertices are a minimal vertex cover, but rather to look at the algorithm by means of which we got to this minimal vertex cover. We started from all the vertices that we had and started to remove the vertices one by one until we can remove no more. And by definition, this is the minimal vertex cover. Okay. So let's similarly find maximal matching in this graph. So I will use the same graph, just use a different color. Maximal matching. So again, to remind you to find the maximal solution, here is our algorithm. You start from the empty set, which is obviously feasible, and add edges one by one until you can add no more. Because if you add more, then you will violate the requirement for the edges to be the matching. Okay, so this is our matching. There is nothing in the graph, no edge is in the matching. That's a matching. It's not a particularly good matching, but that's a matching. Let's start adding edges one by one. I don't know, let's start put this edge in. This edge alone is a matching because there is no vertex which is incident to two edges in the matching. So, well, that's a possible matching. Let's continue adding edges. So I cannot add this edge because if I do, then at this vertex we would have two matched edges coming in. I cannot this edge, I cannot this edge. So I cannot add any edge to which this chosen edge would be incidented at a vertex. But I can add some other edge. I don't know, I can add this edge. Okay, these two edges, the two blue edges in the graph, they form a matching because they don't come to a single vertex. Okay, can I add more? Are there any other edges that I could add? Well, I can not add this edge. I cannot add this edge, this. I cannot add any of those, but I think I can still add this one. Okay, so these three edges, they form a matching. Can I add any other edge? No, as we already checked, none of these edges can be added. So this solution constitutes a maximal matching. Whatever these edges are, 2, 3, 1, 5, 6, 4. Okay. Again, a very easy algorithm to find a maximal matching. Start from the empty set and add edges one by one until we can add no more. There you go. Okay, so we have 2 minutes remaining recording. Let's do a small graph to do a very quick example of maximal matching and minimal vertex cover. So here is my graph. It's a very small one. Minimal vertex cover in it. We start from all three vertices. That's a vertex cover. Can I remove one? Well, let me remove an arbitrary one. Yes, of course I can remove one. Now I cannot remove any more because if I remove this one, then this edge becomes uncovered. If I remove this one, then this edge becomes uncovered. So there you go. This is a minimal vertex cover. Okay. Small graph running fast. 1 minute remains. Let's find the maximal matching. What we have now, the empty set, no edges in the matching, is a matching. Let's take an edge in the matching. This one, for instance. Can I add anything else? I cannot add this edge because I will have a conflict at this vertex. I can not add this edge, for I will have a conflict at this vertex. So done. This is a maximal matching and a minimal. So okay, we looked at finding the minimal and minimal vertex cover and maximal matching. Now I'm clicking to I will click through a couple of slides in the slides. So in the next slide, again, I will not show you this video, but just for information, there is also a video which you can watch on finding maximum and maximal matchings. What I want to do now is the approximation to the minimum vertex cover via maximal matching. And to motivate this approximation, I want to ask this question. How good can be minimal and maximal in comparison to minimum and maximum? So we know that the minimal is not necessarily minimum, maximal is not necessarily maximum, but how far from the optimum can we be? In particular, and I'm now starting to draw on the Jamboard. I will use the black color for the graphs. I want to draw a graph like this. Such graphs are called stars, well, because they look like stars. And I want to ask you, what is the minimum vertex cover in such a graph? What is the size of the minimum vertex cover? How many vertices do you need in order to cover all edges of a star? Maybe you can give the answer in the chat or otherwise. The recording. So this vertex, no, let's say it's vertex 1. So vertex 1 is a vertex cover, and that's a minimum vertex cover because, well, look at any edge. One of its endpoints is incident to the vertex 1. So the size of the minimum vertex cover, and I will just say min vertex cover because min usually means minimum. So the size of the minimum vertex cover is 1. Okay. On the other hand, if you want to find the minimal vertex cover, you may be extremely unlucky. So imagine that you took all these vertices, call them leaves, all these vertices in a vertex cover, and you didn't take vertex 1 in your vertex cover. Okay, so all these vertices are in your vertex cover, but this vertex is not. This is still a vertex cover. I mean, again, every edge has one of its endpoints covered. The bad news is that this is actually a minimal vertex cover. You cannot remove any of these vertices from the vertex cover, because as soon as you remove one, I don't know, if you remove this vertex, well, this edge becomes uncovered. So all these vertices must stay in a minimal vertex cover, and you can see that this minimal vertex cover is really, really bad in comparison with the minimum vertex cover. Okay, so minimal not only doesn't give you the minimum, but can also be arbitrarily bad in comparison to the minimum. The situation with maximal matching is slightly better. You can prove that maximal matching always gives you a true approximation to the maximum matching. But what I want to do now is go back to these slides that we have and tell you how we can find a good approximation, in fact, a true approximation to the minimum vertex cover. And interestingly, you can find a true approximate minimum vertex cover using maximal matching. So this really gives you the connection between vertex covers and matchings. And here is the algorithm. So you find the maximal matching. Okay, so let M be, a maximal matching. And you take the endpoints of the edges in M as your cover. And the claim is that, first of all, this way you will obtain a vertex cover. That is, every edge will be covered. And moreover, the size of the set thus obtained will be at most twice the size of the minimum vertex cover. Okay, so first the algorithm, we'll look at this picture and then we'll have a proof. So just at this picture, so these two purple edges, this and this, are a maximal matching. Well, you can check, you cannot add any of the edges without violating the matching property. So these two purple edges are a maximal matching, and according to the algorithm, you take the endpoints of these edges into your vertex cover. Okay, so these four red vertices are a vertex cover. And the claim is that the size of this is at most twice the size of the optimal vertex cover. And this is kind of obvious, right? I mean, every edge in the matching needs to be covered by at least one vertex, right? If you want to have a vertex cover, then, well, this edge must be covered by a vertex, this edge must be covered by a vertex, and every edge in your maximal matching must be covered by a vertex. And since edges in the matching are independent, right? You will never have two matched edges come into a single vertex. That's not allowed in the matching. You know that every edge in the matching will have to be covered by a separate vertex. Maybe this edge covered by this edge covered by this, but you cannot have a single vertex covering two edges in the matching. And so you know that the size of the vertex cover is at least the size of the matching. And what you are producing is something which is twice the size of the matching. So the vertex cover that you are producing, the vertex cover that you are finding, has as many vertices as there are edges in the matching times 2, because for every edge in the matching, you take both of its endpoints into the vertex cover. So the size of the vertex cover is equal to 2 times the number of the edges in the matching. Minimum vertex cover, or any vertex cover, has to be at least as large as the number of edges in the matching, which means that your vertex cover is at most twice larger than any vertex cover, in particular twice larger than the optimal vertex cover. Okay, so that's how you prove the approximation factor 2, that you will not be much worse than the minimum vertex cover, while you can get at most by a factor of 2. And the reason why you are producing a cover is the following. Assume that in a graph, you have an edge which is not covered by the vertex cover obtained from this algorithm. Well, it means that this edge is not in the matching. And if it's not covered, it means that none of these edges incident to these vertices was in the matching. Because if any of these edges were in the matching, you would have picked both of its endpoints into the vertex cover. But if you have an edge and to both of its endpoints, you have no edge from the matching that would be incident, then you can add this edge to your vertex to your matching, and hence you didn't start from the maximal matching. Okay, so that's the proof of why this set obtained by this algorithm, why this set indeed constitutes a vertex cover. Every edge will be covered. If an edge were uncovered, then you could have added this edge to your maximal matching. Okay, So that's the algorithm. Let's now again do it on, I don't know, say on the next page in the Jamboard. So we have one example of how this algorithm runs over here on this graph. Two purple edges, yes, they are a maximal matching, and their endpoints constitute a vertex cover. Let's do another example now on the Jamboard. I'll try to draw another graph. No, maybe something like this. Okay, that's a graph. So in this graph, let's first find a maximal matching. Remember, you don't have to find the maximum matching. It's enough to find the maximal matching. How do you find a maximal matching? Well, very easily. We take the edges one by one. Let's take this one. Okay, now I cannot take this. I cannot take this. Which one can I take? Well, I can take this one. Right. Yeah, could have taken any other. Well, now I cannot take this one, I cannot take this one. So I claim that this is a maximal matching, right? I cannot add any edge to it. Okay, and according to the algorithm, we take the endpoints of the edges in the maximal matching and put them in. So the red things are a vertex cover. And indeed, we can check that it's a vertex cover. This edge is covered by, this vertex. Yeah, this edge is covered by this vertex, and so on. So of course, the matched edges are covered from both sides. Well, that's by our algorithm. So maybe it wasn't optimal. So we have a two approximate vertex cover. So this is two approximate vertex cover, the red ones. Well, it has 4 vertices, and maybe you could have gotten with 3. I guess in particular, this vertex cover is not minimal. What you could have done, maybe you could have removed this vertex, and that still would be a vertex cover, whatever. We are not trying to make it minimal afterwards. All we are saying is that this way, by taking the endpoints of the matched edges in a maximal matching, we get a two approximate vertex cover. That's all we need. Okay. So any questions on this approximation algorithm or anything else? Okay, so we were talking about vertex covers and matchings in the graph, in particular minimum vertex cover, minimal vertex cover, maximum matchings, maximal matchings. A notion for the vertices, which is somewhat similar to the matching, is the notion of the independent set. Okay, so an independent set is again a subset of vertices, just as a vertex cover. And the property is that any 2 vertices in the independent set are not connected by an edge. Okay, so if you take any 2 vertices, U and V, in the independent set, there should not exist an edge between them. Okay, UV is not part of the edges of the graph. So it's kind of similar to the definition of matching, where you didn't want any 2 matched edges, quote unquote, connected by a vertex, or you didn't want these 2 edges to be connected via a vertex. In the independent set, you want that any 2 vertices in the independent set are not connected by an edge. That's why it's kind of called independent. If the edges in the graph show some kinds of dependencies between the vertices, then you want the set to be independent, meaning that all the edges should be absent between the vertices in the set. Okay, so it's similar to matching. So it's finding an independent set is a packing problem. A set which has no vertices, like an empty set, is an independent set. Yes, because no 2 vertices out of the empty set of vertices are connected by an edge. And as with many, or actually with all packing problems, The interesting thing is to find the maximum independent set. And again, as with many packing problems, there is no efficient algorithm for that. But of course, there is an algorithm to find the maximal independent set. Well, you start from the empty set and start adding vertices one by one until you can add no more. And here are two examples on the same graph. So these three blue vertices form an independent set. There is no edge between these two, no edge between these two, no edge between these two. So they are an independent set of size 3. And here is a maximal independent set. Well, there is no edge between these two vertices, and you cannot add any other vertex so as to keep the set independent. Like if you add this vertex, well, you will have an edge here. You add this vertex, you will have an edge here, and so on. Add this vertex, well, you will actually have two edges, both this and this one. So no matter which vertex you add, if you do that, you will stop having an independent set. Hence, your independent set is maximal. Again, not necessarily maximum, because as you can see here, you have only 2, but you could have as many as 3. So you are not getting the maximum, but you are getting a maximal. Same thing as with matchings, but kind of vertices instead of edges. So the reason why independent set is interesting, well, there are many reasons. In many cases, you want to find independent sets, but one of the important applications of independent set is scheduling, in particular job scheduling. So you can have a set of jobs, and the jobs may have some compatibility, like certain sets of jobs may not be executed simultaneously, maybe because they require, the same person or the same machine or whatever. And what you can do in this case is you can form a graph on jobs. So you can form a graph whose vertices are your jobs and whose edges connect jobs that conflict. So if two jobs cannot be executed simultaneously, for whatever reason, because they require the same person or the same machine or something else, you connect them by an edge. And then finding a subset of jobs that can be executed simultaneously is equivalent to finding an independent set in this graph. And this is how we're going to work with job scheduling. So here is an example. Maybe you have 6 jobs, and every job has to be executed on a certain machine, and every job has to be executed by a certain person. And what you can do is, well, you can form a graph on these jobs. So 6 jobs, hence 6 vertices in the graph. And then you can check the pairwise conflicts and add edges whenever you have a conflict between 2 jobs. So for instance, job 1 conflicts with job 2 because they require the same machine. So there is an edge between 1 and 2. Job 1 also conflicts with job 3. Yes, it does, because they require the same person. So they cannot be executed simultaneously, and so on. Job 1 doesn't conflict with job 4 because they're executed on different machines and by different people, and so on. You check in the pairs of jobs one by one, and now 5 and 6 seem compatible. Different machines, different people. I don't know, 3 and 6. There is edge between them. Why? Because both of them require the same person working, and so on. So you form in a graph where the vertices are the jobs and the edges are the conflicting jobs, connect conflicting jobs, and trying to find an independent set in such a graph. And you will not necessarily find a maximum independent set, but finding a maximal is already something. Like for instance, the vertices 1 and 4, well, they're not connected by an edge, so they are an independent set. Vertices 4 and 6 are an independent set by themselves. 1, 4, and 6 would not be an independent set altogether because there is an edge connecting 1 and 6. But separately, these are independent sets, 1, 4, and 4, 6. 5, 1 is also an independent set because there is no edge connecting 5 to 1. 2, 5, 6 is an independent set. So 2, 5, 6. None of them is connected by an edge. So that's an independent set, and so on. Okay, so that's the way how to choose a set of independent jobs, the jobs that can be executed simultaneously by formulating it as an independent set in the graph coordinate. And some graph, I'll draw the graph with black to be consistent. Maybe like this. Okay, independent sets. Well, you already have an independent set, right? The empty set is an independent set. So maybe this one and this one. This is an independent set because these two are not connected by an edge. Is it a maximal independent set, or can I add something else? Can I add another vertex to this set while keeping the independence? I think yes, I think I can still add this vertex. I cannot add this one because there will be edges. I cannot add this one because there will be edges between vertices in my set. I cannot add this one. So this is a maximal independent set in this graph. Okay, as simple as that. And for the last example, an example of job scheduling, I don't know, let's come up with some jobs. 1, 2, 3, 4. So these will be jobs. These will be machines. Maybe this is executed on machine 1, machine 1, machine 2, machine 2. Maybe this is executed by workers, I don't know, A, B, B, and C. So let's find the maximum, or a maximal or a large set of jobs that can be executed simultaneously. We have 4 jobs, so we form a graph on 4 nodes, 1 node per job, 1, 2, 3, 4. Now, let's look at job 1. It cannot be simultaneously executed with job 2 because they share the same machine. I think job 1 can be executed simultaneously with job 3. I don't see any conflicts. Job 1 can be executed simultaneously with job 4. I don't see any conflicts. Job 2 cannot be executed simultaneously with job 3 because they require the same person. Job 2, I think, can be executed together with job 4. No conflicts. And finally, job 3 cannot be executed together with job 4 because they require the same machine. Okay. So this graph is the graph representing this instance where you have jobs at the vertices and you have edges indicating conflicts between jobs or jobs that cannot be executed simultaneously. And now we can start picking up independent sets in this graph to see which jobs could be executed simultaneously. Well, so one independent set is, I don't know, job 1 and job 4. And this is a maximal independent set. Another independent set, let me use another color, I don't know, job 1 and job 3. Again, it's a maximal independent set. You cannot add any more. Job 2 and job 4, yet another maximal independent set. I don't know if there are any others, but hopefully you get the idea how to pick maximal independent sets. As with any maximal solutions, finding them is pretty easy. You start from empty and you add until you can add no more. That's all you need to do.